First question is, what are their maximum size? Many of you did the same size cube, right? I see many of them about the same size. You tore off one and then you made 4 squares with it. Do you think it's possible to make a larger cube?
Yes.
There actually is. We showed that there is. Someone did one that there is. But the real question is, what's the biggest cube you could make? And really, you're figuring what's the biggest 6 squares you can make out of one 8.5 by 11 piece of paper. And the sub question is, with a ruler, if you had a ruler, what's the biggest you can make? And also, with no ruler, if you could just fold and just tear along the folds. Do you understand that this isn't necessarily the same thing? Using a ruler, you might come up with a plan and measure, right? But can you always measure when you fold?
No.
No, you can only fold like one edge to another edge or diagonals. It's much different. So I want you to think about that thing, okay? Okay. What we're going to go into is volumes of these shapes. Specifically, you see it. You'll be able to see it a little better now. First thing you do, you have it flat, you fold it, you make it a mountain like that. That's called a mountain fold. What would a valley fold be if I folded it the other way? So that's a mountain fold, and then what you do is you fold them both back, like this one is. So you see that right there? Yay. So you have that one piece, and then you do the same thing again. You do the same thing again, and I'll take a green piece here.
Are you folding one?
I think
The pockets, look, the pockets are up here, so I'm folding it back, and then I'm folding these pieces back. So then what you can do is, the only reason you do this is the only time you'd really fold it like this, is to make this one specific shape. You only fold along the folds you've made, so you fold those two back, and then look, you almost have it, but it's open. It's open, so we're going to close it by taking this last piece.
Are pockets on the outside or inside?
Outside, outside, outside. Pockets are always on the outside on all of these shapes that I make. Can you invert any of these? Yes, but the pieces don't hold together nearly as well. So look, here is this right here. See that right there? So that's how you can do this shape right here, which is great. Nice. Okay, so you asked before though, what about those spikes that like on that big piece right there? What you do is you do the exact same thing. Kids, watch, boys. You fold it across, you fold one of them back and one of them forward. So you see this right here? So I have the piece, I fold it, so there's the mountain fold right here. One of the little legs goes back and one of them comes forward. So if I do this, one goes back, one comes forward. Keep in mind it doesn't matter which one because you can flip it over. Same thing here. I'm going to reverse one of these folds. If I take these two now, I take this and I slide that in, and I slide this in. You end up with one pointy spike. You end up with one pointy spike. You see this pointy spike right there? And then what can you do with 3 of these pointy spikes? Put them together into one part of that big blah, the big cool star right there. So that's a pointy spike. One last thing you can do is make a less, you can make a, I'll call it a less pointy spike, everybody. Shivani, watch please. You start out with 3 pieces this time. You start out with 3 pieces, and instead of doing a mountain fold, you do a valley fold. So you in like this, and then what you do is you fold them both. You fold them both back. So if I do this, if I fold them both back in a valley, both back in a valley, both back and a valley, you end up with something that looks like this. Now watch what you can do. It goes in there like this, turn it, and then the third piece comes in like this. This is the piece you use to make the 12 and the 24 sized one, pieced one. If you fit them together like this, you can make a 12 and you can make a 24. You can also make a 120, but I don't think you want to go that far. It's very hard. So again, we'll call this the little spike, and this is valley like this and back. All of the shapes, all of the closed shapes that I make are all made with the same fold. Meaning if you have a piece and you fold one of them like this, all of them get folded like this. If one of them gets folded like this, the spiky spike one, every other one gets folded like that. It's a replicated piece. It's a replicated piece.
Is that a mountain fold?
A mountain fold is anything that goes up. A mountain fold
So
is
that
anything
is
that will know if it's going up. Like if I turned it over, it would be called it would be called a valley fold. It depends on your point of view. All when up for me is the pocketed sides. So if the pocketed sides are up and it goes up, it's a mountain fold. If the pocketed sides are down, it's a valley fold. You see the pockets right here? You see the pockets?
Yep.
One side has pockets, one of them does not have pockets. Okay, so look, if it's flat in front of you and you see the pockets, everybody, that would be a valley fold. That would be a mountain fold. It's all about reference. If this was up for me, if this was up, ready? Hey, look, there's a valley fold, right? It depends on what is up, right? Totally depends on what's up. Okay, your homework tonight. Okay, so here we go. Pause this for a sec. Okay, so you're trying to find the absolute minimum and absolute maximum, right? So what do you need to find first? Why?
To find critical points.
Yes, to find critical. You're using the derivative to find critical points. So f prime of x is going to be cosine x minus sine x. And remember, you really have to pay attention. It's that interval. That's really, really important that you pay attention to that interval. Okay. Now what?
Now we have to find where it equals 0.
Let's find where it equals 0. So where does cosine x minus sine x equals, where does it equal 0?
0.
Well, that's when what?
Cosine x equals sine x.
Cosine x equals sine x. How could you solve that? What could I do? Bingo, you divided both sides by cosine. Divide by cosine and you get 1 is equal to tangent x. So x is equal to tan inverse of 1. The tangent of what angle is 1? The tangent of what angle is 1 between 0 and pi over 4? Pi over 4. The tangent of what is equal to 1?
45.
45 degrees, because it's root 2 over 2 and root 2 over 2. And every 2 pi multiple. That's correct, right. And actually, every pi multiple, because it could be, if it was negative and negative, right. But we're specifically between here. When you don't have domain limits on trig functions, it gets really funky sometimes. So the answer to this is x is equal to pi over 4. You always stay in what mode unless otherwise told? Please stay in radians. So pi over 4. So that's when the derivative is 0. But, okay, so is there any place where the derivative isn't defined on the domain 0 to 3, pi over 3? No. So this right here is the only extra for the critical points, but what else do you need to test?
Whether it's a max or a min.
Well, no, we do first, okay, so now we do f of pi over 4, right? And we end up with sine of pi over 4 plus cosine of pi over 4. So that's root 2 over 2 plus root 2 over 2, which is root 2. We're not done yet, because we also need to test what? We need to test the endpoints. Don't forget the endpoints. This is huge. You're not done. Endpoints. So you test the endpoints. What are the endpoints? So you do f of 0, sine of 0 plus cosine of 0. What's sine of 0?
0.
0. What's cosine of 0? 1. So this is 1. And then we also need to do f of pi over 3. So it's going to be sine of pi over 3 plus cosine of pi over 3. What's sine of pi over 3? And this is plus 1/2. So that's 1 plus root 3 over 2. So our extreme values are going to occur at each of those places. Our extreme values are going to occur at each of those places. So which one is the max? Yeah, this right, you know that this is about what? You should know in your head that that's about where, go to 3 decimal places, 1.414, right? Well, that's bigger than 1, right? This one right here, that's a little trickier though, isn't it?
It's like
Well, look.
half 2.7 something. No, 1.7.
The point is, how do you justify this without knowing the exact decimals? And the thing is, you don't have to, okay? This doesn't say, if you didn't have a calculator, I would give you a way to know for certain. I don't expect you to know what the square root of 3 is plus 1 divided by 2. Plug it in your calculator, what do you get? You get 1 plus the square root of 3 divided by 2. You get around, sorry, that was not it. 1 plus the square root of 3, enter, divided by 2, you get like 1.366. So, and then let's go back and let's see what the question asks. This is the last thing. Great work, right? So those could be mins or maxes, but which one is the absolute max? The question itself is asking, you don't want to do that. Find the absolute max and absolute minimum. Find the absolute max. So are they asking for x values? Are they asking for...
Yes.
Nope.
No.
Find the absolute maximum, absolute minimum values of f. Are they asking for x values? No, they're asking for y values. They're actually not asking you for coordinates at all. They're not asking you where it occurs, right? So the absolute max is where? Is what value? Root? No.
No, it can't be because.
No. What's the hold on.
Interval is 0 and
3. No, it is root 2. The absolute max is root 2. And what's the absolute min? Sorry.
1.
The absolute min is 1. We could further verify this by verifying if they are local mins or maxes. That's kind of irrelevant to the point. We know that each of these is a min or a max, right? We know that each of them is a local min or a local max. And those are the only places where these mins and maxes could occur. Well, actually, the endpoints, it just terminates there. Yes, go ahead.
Isn't the
0 to pi divided by 3. Let's graph this. So this is from 0 to pi over 3. Now, hold on. Here's the thing. Just because it looks like one thing on your calculator doesn't mean it is what you think it looks like. The resolution on these calculators is... It's not very good, which is really weird because the resolution on these calculators has stayed the same since I was in high school. And I'm old enough that you'd think that it would change. I don't really know. Like, at a minimum...
costs the same?
Well, no. I understand why it costs... I kind of understand why it costs them. I don't understand why they don't make the resolution better on these. That I don't understand. Okay, so what should we change here if we're going to see what that curve looks like? Yeah, so let's go from 0... Let's x-min. Let's go from 0 to what? 2? Is it 2?
Yeah.
So it's going up, it's going up, it's going up, and then what is it doing?
Change.
It is going down. It is going down. So this thing arcs up and then does go down. That is correct. So what's this thing doing? It's going up and then it's going down. What do we know, though? If we take this graph right here, we've figured out this matches what we have because this value right here, when we plugged in 0, what did we get?
1.
Really? When we plugged in 0?
We got 1.
We got 1. You're absolutely right. Thank you. So this right here is 0, 1, right? We know that this point where it peaks out is going to be what? Pi over 4, comma what?
Root 2.
Root 2. And then it comes down right here, and it's pi over 3, comma 1 plus root.
Root 3.
Yeah. All over 2. Exactly. So visually, does it match? Yes. Just be careful when you just look at your calculator because the resolution on these things is not very good. You could change this. I just like seeing the axis down here if you can. You don't have to have that in there. That's totally fine if you don't. Does that make sense, everybody? Some complicated calculus, and then you're going to test the endpoint, and you're like, oh, okay, great. It always increases, so it's going to be the one furthest to the right. You'll be like, But you verified that. I understand it's slightly frustrating when that happens, but to prove that, you really need to look at the function. I mean, things you should look out for, if the derivative is always positive, the function is always increasing, right? If the derivative is always negative, it's always... So if you know it's always increasing, you should just look at the point furthest to the right if you're looking for a maximum and the point furthest to the left. Don't forget basic logic is what I'm saying. Don't forget basic logic. Use the graph of f to estimate the values of s that satisfy the conclusion of the mean value theorem from 0 to 8. So what's the first thing you should do if you're going to do this?
Find the slope from 0 to 8.
Yeah, so from 0, there's the first point. There's 0, comma, f of 0, right? And 8. 2, 3, 4, 5, 6, 7, 8. 8 looks like it's right there. So did they nicely give you integer values here, it looks like?
Yeah.
There's a f of 8. And it really looks like f of 0 is what? Or about what?
4.
I mean, do we know exactly what it is? No. F of 8 is around what?
6.
Is that true? 6. So you want the slope from there to there. You want the slope from those two lines. Okay, between those 2 points. So the slope is going to be equal to f of 8 minus f of 0 over 8 minus 0. What's that going to be equal to? 6 minus 4 over 8, which is equal to 2 over 8, which is 1/4. You can see that visually by doing what? Drawing the line. Let's pick a different color here. Let's go with, I don't know, let's go with a blue color. And let's go with the line here. I'll do my best. So there it is. There's that line. So you need to find the c-value. The c-value lives between what and what?
Between 0 and 8.
Yeah, c,
C.
the c-value, it could be, in this case, there's going to be more than one, but there's at least one because it's a continuous function that's closed on the,
Integral.
it's continuous on the closed interval, and it's
Differentiable.
differentiable on the open. In this case, it really looks like both of those things are satisfied. It's also telling you to do it, so you have to assume that, right?
Yeah.
You can assume that there's no like really tiny dot in there that it just jumps over, right? There's a lot of assumptions you have to make. So what do you do? How many c values does it look like satisfies?
2.
I see 1, 2, 3. I see 4.
Yeah.
Why?
Those curves.
Yeah, exactly. Now I wish. Let's see if I can do this. Oh, dang it! Doesn't let me do that. Oh, it does. Check this out.
What?
That didn't help me. It pasted too much. So the point is, I'll do it right here. It looks like there's one right here, one right here, one right here, and so the c values it's asking for, it looks like it's not 1. It looks like it's about, I don't know. What's it look like that value? It's like, I don't know, 0.75, right? This one looks like it's about 1, 2, 3.25 maybe. This one looks like it's about, I don't know, 4.3. I don't know, and this one is going to be 6.25. You know, I'm not going to grade you to like the 3 decimal places here, right? You have no way of doing it. But if you said, hey, there's 4 values and this is what they are, I would say, yeah, you're absolutely right. That is a good estimate. Does that make sense, everybody?
Okay, so we just estimate that.
Yes, it says that right there. Estimate. It really does. You get so used to coming up with answers to 3 decimal places or in radical form that sometimes it's hard to like let go and estimate. There are ways to make good estimates. This is a good estimate. Why is this a good question?
Because there's a bit of, you have to remember how to, what here.
Yeah, you have to
says.
remember what the mean value theorem says, so you have to figure out what to look for. Is the super accuracy of the end result super important for this question? No. But like, how could you get this one? You might say, oh, there's 1. Oh, there are no values, right? I mean, getting that there are 4 and estimating them remotely properly. Skipped.
It's an alpha. Or
Close, yeah.
it's-
To really prove continuity, you do that in a collegiate math class called analysis. It's functional analysis. It's real analysis, where you need to do epsilon delta proofs. This is something that's in your book. We skip these. It's not on the test. It's a big idea. If we have time, we'll go back to it. It's kind of a neat thing for you to see because when you get to these, if you take more math, it's really helpful if you've seen them before so that they're like, what? No, you need to go get over that hump. Everybody looks at the first and goes, yeah, that makes no sense. No one except like, I don't know, 1 in a million people like, oh, that makes perfect sense. No. So let me just redo this again so you have it in the video. This could do anything you want, but you know it's continuous on the closed and differentiable on the open because it's a car moving. It can't teleport, and it can't instantaneously change velocity. So therefore, the mean value theorem applies, and the mean value theorem tells you that there is at least one c value that gives you exactly what you want. Okay, 4.3 says, for what values of the numbers a and b, those are so going to be integers, right? They don't have to be integers, actually, real numbers. You assume that they're real numbers. Does the function a times x times e to the what power? Bx squared. It's b times x squared. Have a maximum value f of 2 equals 1. So let's just say I gave you this and asked you, please find me the maximum value. How would you go about doing it? What would you do first? Find the derivative. Do we have to worry about endpoints on this one? No. Why? There's no limit on the domain. It doesn't say like from something to something else, right? So let's find the derivative. If we're doing the derivative of this, can someone tell me what the overall rule we're going to have to use is? But before we do the chain, what do we have to apply? Product, right? And the a is just going to stay on the outside. Is that okay? Do you understand that? The first function is x, and the second function is b to the x squared, right? So let's do the derivative of the first, which is 1 times the second, right? Plus the first times the derivative of the second. So I haven't done the derivative yet, but I'm writing it out step by step. Are we okay so far? So again, what rule did we just use? Product. We just used the product rule. We have not used the chain rule yet. So know that that's going to be a times e to the plus x times e to the bx squared times d dx of what? Bx squared. What do we just use here? Now we just use the chain rule. We had to kick out the derivative of the inner function. Now we're just cleaning it up. Well, a little bit differentiation. E to the bx squared plus x times e to the bx squared times what? Times 2bx. Exactly, right. What can we factor out in the middle here? Just so we can, I like factoring whenever I see things. What can I factor out? E to the bx. So what this becomes a times b to the e bx squared times what? 1 plus what? 2bx what?
Yeah,
Yeah, the first B.
Thank you. That's a really important thing.
Yeah.
And this is f prime of x. Are you okay with that?
Yeah.
So we know that we're looking for what? A max, right? We're looking for a max. We're looking for a max. We want f of 2 equals 1 to be the... So what is the max value? What is the max value? 1. The max value is 1, and we want it to happen at what? 2. Now here's the thing. Max and mins can only occur at critical points, right? They can only occur at what? Critical points. Okay, so do we have to worry about endpoints here? No, so only the points we're looking at where the derivative is equal to
0.
So let's look at this statement here. AE bx squared times, I don't know why the tops got cut off there, 1 plus 2bx squared, and we want that to equal 0. Right? We want that to equal 0. When what is true?
X equals 2.
When x equals, excuse me, we want the derivative, yes, we want the derivative to equal 0 when x equals
2.
So let's plug in 2. So we have a times e to the what? 4b times 1 plus 8b, right? So we plugged in, this is important, when x is equal to 2. How do you make that equal 0? What's the only way to make that equal 0? Okay, a or what? B equals what? Negative 1/8. Now here's the thing. I think it tells you a and b... Well, hold on. If we let a equal 0, what happens to our original function?
0.
It becomes really boring, and it makes it not true, because can f of 2 well, actually, no, it could equal 1, right?
Yeah.
No. If a is 0, the whole thing zeroes out.
Yeah.
Right.
So this, not an option, right? Do you agree?
Yeah.
So b has to be... b has to be negative 1/8. b has to be negative 1/8, because if b is negative 1/8 and a does not equal 0, we know that the derivative will be 0 at 2, right? But here's the thing. We know that when x equals 2, the derivative is 0, but we want, when x equals 2, we want the function to equal what?
1.
When x is equal to 2, we need the function to equal 1. So what do we do with this? We have the original function, yeah, equals ae to... Did I get this right? Did I get that right? ax, thank you. Ax e to the... Like that, right? So we know that when x is 2, what has to be true?
Y is equal 1.
Exactly.
Equal 1.
So we say 1 is equal to a times what? E to the... Oh, we already figured what b has to be, right? B is what?
Negative 1/8.
And a, what is x again? 2 squared is? 4. So we have 1 is equal to 2a e to the what? Negative 1/2, correct? We okay with that so far? So we have 1/2 is equal to a e to the... What does negative 1/2 mean?
1 over the square root of
So we know a over the square root of e is equal to what? So what does a equal?
root e over 2.
Yeah. So a is equal to root e over 2, and b is equal to negative 1/8. You have to use logic and think about this. Yeah, oh yeah, a is 0, but can that work?
Nope.
No. That satisfies our derivative constraint, but does that satisfy our original function constraint? No. So you know that b is negative 1/8, but then you know the function has to equal 1 when x equals 2. Could you have done this in a different order? Potentially, you could have done this, but then if you didn't know b was negative 1/8, could you solve for a?
No.
No. You could not have.